Today we are going to see more interest formula. Last lecture we saw the equivalent payment, that's mean a uniform series. Today we are going to see more formula. It's about arithmetic gradient. So suppose that we have a cash flow like that, as you see here, and we would like to find the present value of this cash flow. So we have year number one, there is no payment, and year two we have $20. Year three we have $30, and year four we have $20. The interest rate is 15%. So here we have three different solutions at which we can solve this problem. First, since we have irregularity in this cash flow, so we can calculate the present value for $20, bring it here, the present value of the second payment, and we bring it here, and the third payment, year four, we bring it to here as present value. So here we can get for solution P, which is the present value for the whole cash flow, will be P1, which is the present value of the first $20. P2 is for the $30 present value, and P3 is the present value for $20. So here we got 20 for the P1, P looking for P given F, because it's 20 is this one is considered as the future value 20. So it's looking for P given F 15%, 2 years. So here from the first 20, this first 20, this one, we have 2 years, 1 year, 2 years, plus $30. This is the second amount, multiplied by the factor looking for P given F 15%, 3 years. For $30 here we have 1 year, 2 years, 3 years, and last $20 is multiplied by looking for P given F $15, 4 years. So when we calculate P1 plus P2 plus P3, we get $46.28. Now the second solution, we can write the relationship between P and F in the diagram is P. If you have P, it will be the future value multiplied by the vector, and the factor looking for P given F $15, 15%, 4 years. So the final value here, it will be for the whole cash flow, it will be here, F. F. So we compute the future sum of the three payments as follow. So here we are going to calculate the future value of 20, after that the future value of 30, and after that the future value of 20. So since 20 is fourth year, so there is no future value, it will be counted as $20. So here we have to calculate F, which is F1 plus F2 plus 20. So F it will be 20, looking for F given P 15%, 2 years. So this is for the first 20. So we have 1 year, 2 year, and after that we have 30, looking for F given P 50%, 1 year, plus 20, which is considered as future value. So combining the two equations, we have P equal to F1 plus F2 plus 20, and this is the future value. We have to bring them to the present value. So we multiply by P, looking for P given F 15%, 4 years. So we get the same amount. If we calculate, we get the same amount that we found here. The third solution is we calculate P, it's 20 multiple, so we distribute on since we have here 20, 30, 20, so we can consider that we have 120, 20 here, 20 here, and in the third year we have 20 and $10. So we have a uniform series. After that we add the 30 and we can get the total present value. So it's a 20, looking for present value given A, 15%, 3 years. So we have 3 years here, plus 10, plus 10, the $10 from 30, $10 from 30 here. P given F, looking for P given F, 15%, 2 years. But here it's calculated based on the present value in year 1. So we have to bring in year 2. So in this case we have we multiply by the factor looking for P given N 15% 1 year. So we get the same amount as solution 1. So this is 3 different solution. I focus on the last solution because in the last solution we consider that we have a uniform series and there is a $10 that is exceeded here. So we have to count them at $10 here. Okay, and we have uniform series. The uniform series, we have the present value P1 here. Okay, and after that we bring P1 to P by this factor. Okay, now arithmetic gradient. So today we are going to see in detail the arithmetic gradient. The cash flow series may not of constant amount A, because in the first part we saw that the cash flow it can be uniform series with a constant amount A. Instead there may be a uniform increasing series. So here we have increasing series. It's not uniform series but it's increasing series. So here we get if you look in this gradient, the cash flow of this form may be resolved in 2 components. So for example you have here A, the value A plus G, A plus 2G, A plus 3G, A plus 4G. So look carefully, we start by year 1 is A, after A plus G, so the amount of increase is G. A plus G, A plus 2G, A plus 3G, A plus 4G. So this cash flow can be divided in 2 components. If we consider A, uniform series A, so we get that this cash flow is a uniform series A, A1, A, year 2A, year 3A, year 4A, year 5A. So we have plus the remaining. So here when we subtract A from A we get 0. So that's why we have 0 here. After that, A plus G, we substitute A, we get G. After that, A plus 2G, we subtract A, so we get 2G. After that, A plus 3G, we subtract A, we get 3G, and the last one we get 4G. So please look carefully to this cash flow. The cash flow starts from year 0. Year 1 should be 0. After that we have G, third one 2G, fourth one 3G, fifth one 5G. So as you see here, it starts by 0 at year 1 and each year it increases by G. So if you get, when we divide the cash flow, you get a uniform series like that plus a cash flow like that, that means 0, G, 2G, 3G and 4G. This is we call it arithmetic gradient. So G is the change from period to period, and because the gradient G series normally is used along with uniform series A, we already have an equation of P apostrophe, and we need to derive an equation for P double apostrophe. In this way we will be able to write P, which is the present value for the whole cash flow. It's P, and after that we have P apostrophe, and here P double apostrophe. So P is P1 plus P apostrophe plus P double apostrophe. So the P apostrophe is the uniform series, so we calculated as what we saw before. So it's A multiplied by the factor looking for P given A, I percent, and period. So in our case it's 5 period. Plus G for the second cash flow, G multiplied by P given G, I, N. So this equation or this factor is in the formula sheet, so you can go and see the equation. So arithmetic gradient present flow, P, it's P, and the factor P, looking for P given G, I, N is 1 plus I to the power of N minus I, N minus 1 divided by I square 1 plus I to the power of N. And the arithmetic gradient uniform factor is A divided by G. A, looking for A given G, I, N, it's 1 over I minus N over 1 plus I to the power of N minus 1. So we can calculate from the gradient uniform series as uniform series, or we can calculate as a present value. If we are looking for the future value, we can from this factor we can convert it to future value. Now let's make an example. Maintenance cost of the car for the first 5 years has been estimated as given. So this is the maintenance cost of the car. Assume the maintenance costs occur at the end of each year, and that the bank pay 5% interest. How much should the car owner deposit in the bank now? So okay, so the first year he pay for the maintenance 120. In the second year 150, in the third year 180, in fourth year 210, and in the last year, fifth year, is 240. Okay, the cash flow, as you see here, the cash flow may be broken into two components. So we are looking how much the owner of the car should deposit in the bank with the 5% interest to get the maintenance cost for 5 years. So the first year he should pay, or he should get from the bank 120. He should the second year he should get 150, third year 180, the fourth year 210, and the last year 240. So we are going to look for the amount that he should deposit in the bank to get at each year the amount of cost of maintenance cost. So here it's as you see here it's here, if you look carefully, we have 120, which is considered at A. 150 is A plus 30. 180 is 120 plus 60, so it's A plus 60. This is A plus 90, and this is A plus 1. 120. So there is an increase of $30. So we can divide this cash flow in one cash flow with a uniform series 120. So we get here uniform series 120. Okay, and after that we have 0 in the first year, because we subtract 120 from 120, we get 0. The second year we have 150 minus 120 is 30. Third year is 180 minus 120 is 60, the fourth year 90, and the last year 120. So as you see here, it's a arithmetic gradient with increase of 30, so G is equal to 30, and we have, as I said before, the first year should be equal to 0. So we have exactly arithmetic gradient. So to calculate the present value, we have to calculate the present value for the uniform series here, and after that we calculate the present value for the gradient. So here the present value is A is 120 multiplied by the factor looking for P given A 5% 5 years, plus G, which is 30, multiplied by the factor looking for P given G 5% 5 years. So from the table, there is a table at the end of the textbook with different factor, but we can calculate using the formula seen in the previous slide. So now that the value of n in the gradient factor is 5 and not 4, in deriving the gradient factor we had n minus 1 terms containing g. So as you see here, we have 5, we have only 4 containing g, the first one is 0. Here there are 4 terms containing g, thus it's n minus 1, 4, so n is equal to 5. So we can substitute the value. For A we have 120, P looking for P given A 5% 5, plus 30, the value of G here, P given G 5% 5 years. So we get $766. So he should deposit in the bank in the beginning of the first year, 766. So he can take from the bank each year the maintenance cost of his car. He should deposit $766 in the bank now. So this is an example of arithmetic gradient. Another one is on a certain piece of machinery, it is estimated that the maintenance expense will be as given. What is the equivalent uniform annual maintenance cost for the machinery at 6% interest rate? So here we are going to look for the uniform series. In year 1, the cost of maintenance is 100, in year 2 is 200, in year 3 is 300, and year 4 is 400. So if we draw the cash flow, we have 0. Year 1 is 100, year 2 is 200, year 3 is 300, year 4 is 400. So we would like to write or transform this cash flow to uniform series A. That means he pay every year the same amount. So for example here we can calculate the uniform series. So here it's a arithmetic gradient with increase of 100. So we can divide it to uniform series 100. So we get 100 for the 4 years, and after that the remaining will be, for year 1 is 0, for year 2 is 200 minus 100 is 100, for year 3 is 200, for year 4 is 300. So here we get a uniform series here, and after that we have a gradient starting by 0, and the gradient for G, the increase is 100. Okay, so to transform this cash flow to uniform series, we have already one part is already transformed to uniform series. We have just to transform this cash flow to uniform series. After that we can add together. So the uniform series A will be 100 plus 100, which is G, multiplied by the factor looking for A given G 6% for a year. So this is given in the formula sheet. So we can calculate, and the equivalent uniform annual maintenance cost will be $242.7. So here the cash flow is transformed to uniform series plus arithmetic gradient. The uniform series is already ready, so we have just to calculate the uniform series of this gradient. We are using this factor as you see here.